maybe, whatever. We're trying, you know, sometimes you just got to do the best you can. So, starting with questions. I think the last time I'd asked you guys to work on this was homework 4, but if you had other questions older than that too, that's okay also. Just kind of let me know whatever you're thinking about. Or maybe you don't have any questions at all. That's okay too, but I feel obligated, especially if you're missing Tuesday, of providing an opportunity to kind of, you know, fill in some of those blanks and answer some questions and do some examples if you guys need it. So just shout them out and holler at me if you do, and if you don't, that's okay too. You know, no pressure. Okay then. Well, if something comes up as you're working on things and you decide that maybe you want to go back. Oh, Maddie.
Can you do number 3, please?
Sure. So I would start here by looking for the greatest common factor. So 1280, I notice, ends in a 0, so it's clearly divisible by 5. So the first thing we looked for was the greatest common factor. We can pull out a 5x. That's x to the 8th minus 256. And that's 2 terms. And the first thing I'm going to look for is a difference of 2 squares. Since the exponent there is even, I feel pretty good about that as a strong possibility. And the square root of 256 is 16, so that does fit the mold for a difference of 2 squares. So I can write that as x to the 4th minus 16 and x to the 4th plus 16. And then I still have that 5x floating out front. X to the 4th minus 16 is also a difference of 2 squares. Minus 4 x squared plus 4. And x to the 4th plus 16 isn't a difference of 2 squares because it's addition. And it can't be a sum or difference of 2 cubes because the exponent isn't divisible by 3. So that one can't change. But I do need to go back and check the x squared minus 4 and the x squared plus 4. X squared minus 4 is definitely a difference of 2 squares. X squared plus 4 is not, though, right? Because it's an addition problem. And it's not a sum or difference of 2 cubes because the exponent isn't divisible by 3. So this is as good as we can do. I know x minus 2 and x plus 2 can't be factored anymore because they're linear. I didn't say that expressly before I started putting a box around it, but I'd be surprised if you guys tried to factor something like that, right? That's pretty obvious that there's nothing more we can do on that. Edmund?
So why is x to the 4th plus 16 not a difference of 2 squares?
Because it's not a difference. It's not a subtraction problem, right? So it has to be subtraction in order to be a difference of 2 squares. Cubes, there's a sum of 2 cubes and a difference of 2 cubes. They have different factoring patterns, just slightly. But you can do both of those. But squares, it's only subtraction. Yep, good question. Again, making sure we're clear on all those details. There's a lot of things going on, so it's always good to have that. Maddie, did that get you what you needed? Okay. Yeah, catching that 256 is 16 squared was probably the sticking point there. Or maybe just remembering to do the greatest common factor. Sometimes we skate past that. Since it doesn't happen that often, it's easy to forget to check that. And if you did, maybe that problem's a mess if you don't. Okay. Anybody else? Happy to do more, but it's okay if you don't need it. Alrighty. So we'll kind of take some steps forward now. So again, what we're going to do, last time we talked about kind of how to do these sorts of problems, right? Where it's something we can't factor with the factoring tree as it's currently written, but I might be able to do a synthetic division and then get something that I can use the factoring tree on to deal with it. Now, in these problems, like in number 5, we gave you a starting place you know, we told you one of the factors that you can use what we're going to deal with today is, what do we do if we take that away? So what can we do if we take away one of the factors? Well, we'd have to find a factor, right? And right now, with no extra guidance, do we have any reason to suspect anything could be a factor? So it's a purely guessing, right? How many choices do you have of possible factors? Infinitely many, right? That's a pretty bad guessing game. So our goal here over the next 2 lectures is going to be to improve our odds of guessing a factor. Now, we'll do a really good job to the point where there's not going to be really that much of a guess involved. I would say that if you understand what's going on here, 90+% of the time you're going to know exactly what factors will work and what won't. You'll still need to do the synthetic divisions and stuff, but we're going to remove most of the guesswork out of the kinds of problems I'm going to ask you to do with the tools that we're going to develop over the next 2 lectures. So we're going to kind of we're going to develop the basic outline here today in class. And in the next lecture, we're going to start worrying about some of the weird things that can happen and how to deal with some weird stuff. Everybody okay with that? But that's kind of the plan. Does that everybody feel okay about where we're going? So the whole goal here is trying to figure out what factors I can use to do the synthetic division. And we'll keep doing those synthetic divisions until we get to something we can get back on the factoring tree track with. And that's kind of that's the basic outline. Okay, so the things that we can't use the factoring tree for, we'll do some synthetic divisions until we can get something that we can use the factoring tree on. And the whole skill involved here is figuring out the factors to use. Because as you saw in 5 through 8, they're really not that much more difficult when you add in like a synthetic division and then turns into a factoring tree problem, right? Not that big of a deal. The skill involved here is going to be figuring out the factor to use to do this, or factors. You might have to do more than one synthetic division. But that's the idea. Everybody okay with that notion? So again, I like to, especially for something like this where the process is kind of a long and complicated one, where there's going to be a lot of tools that we're going to be using to kind of make some good guesses. I like to try to give you an outline of where we're going and what we're trying to accomplish here before we get going, because I think it helps make the lecture a little bit easier to follow because you can see what we're trying to build towards a little bit easier. Okay. So that's kind of the question we're going to be looking to answer over the next 2 lectures, is how are we going to pick these factors that we're going to try to do the synthetic division with. Okay, so we're going to start with some theorems here, and then we're going to do a couple of definitions and kind of trace out the basic procedure, and then next lecture we'll come in and add in some of these extra tools that'll help cover some sticky situations we can land in. And we'll kind of outline what those sticky situations are maybe at the end to kind of, prep us for the next time. The first theorem that we're going to talk about, let's get out of the red, right? That's probably the hardest color to read in general. Algebra. And as you might have guessed from this title, this is a pretty important result here. Probably the most important algebraic result of like the Renaissance era. This was something that mathematicians had worked quite hard on for several hundred years before somebody finally was able to do it. Really the best mathematicians of the age all took turns taking a crack at this, and nobody was really successful at doing it until a German fellow came along by the name of Karl Gauss, and he eventually was able to complete this proof and was maybe the most important mathematician of like his era, like in the 1700s. Now it's a foregone conclusion that eventually this was going to be taken care of, because not too, within another 100 years or so, calculus is invented, and this becomes a much easier proof with calculus tools, but without it, it's a considerably more difficult thing to prove. But it's a very simple statement. And basically all it says is that all polynomial equations are solvable as long as you're allowing for imaginary solutions. And these are some of the hardest kinds of proofs, where you need every situation. Like that's a difficult thing to prove, especially when you're not putting any restrictions on the kind of coefficients your polynomial can have. But that's the proof, I'm sorry, not the proof. We're not going to talk about the proof in the class. But that's the statement. Useful to us is the corollary to that fundamental theorem of algebra. States the number of solutions to a polynomial equation of the form f of x is equal to 0, where f of x is just a polynomial. The number of solutions is going to be equal to provided we count imaginary solutions and multiplicities. Now we know what an imaginary solution is here, right? That's not a big deal. This term multiplicity, I don't remember if I used this in last semester or not, but let's talk about what that is one more time, even if I did. Most of you probably have forgotten, because it would have been just like once in passing. But it's a situation we've already encountered in first semester, so it will not be difficult to understand what we mean by that. So in first semester, you might have solved an equation where something like this happened, right? X plus 2 times x plus 2 is equal to 0. Well, when we do that, we get two solutions. We get -2 twice, right? Everybody recall something like this happening in first semester? Would not have been uncommon for this to happen. So what we say is the of 2. Since that solution occurs twice, it counts as two separate solutions according to this corollary. Is everybody okay with that idea of what I mean by a multiplicity? So what we're saying is that the degree of the polynomial tells you how many solutions it can have, as long as we're counting the imaginary solutions and the multiplicities. it's going to be exactly. If it's not, if we're not counting those things, then the degree creates an upper bound on the number of solutions. Like you can't have more than the degree. You could have less if you're not counting imaginary things, or you're not counting multiplicities as separate solutions. Then it's an upper bound, which is still good, right? It's a limit to how many solutions you could have. But if you're counting those, it's tight. So it's exactly equal. Everybody okay with that idea? Okay. The next theorem we have is called the factor remainder theorem. And this is what we used in the previous homework when we did the synthetic division. And this says x, or I'm sorry, I want to write this as an if and only if. X minus a is a factor of a polynomial f of x if and only if f of x divided by x minus a has remainder 0. So this was basically the tool that allowed us to do the synthetic division and turn it into a factor, right? Or into a factored form. Okay. One more tool we have before we kind of make a summary and see what we can do with this stuff. So the last theorem that we're going to talk about today is called the rational roots theorem. Let's see, we should say a polynomial f of x with integer coefficients maybe we should say 4 the rational solutions to rho are of the form x equals plus or minus a factor of the constant term divided by a factor of the leading coefficient. So let's do just an example of how we apply this. So let's say we have this polynomial 6x to the third minus 10x squared plus 6x minus 35. What the rational roots theorem is going to tell us are the possible to that polynomial set equal to 0. Now, to come up with those possible solutions, I need to know the constant term. In this case, that's negative 35. And the leading coefficient, which in this case is 6. The factors of the constant term are 1, 5, 7, 5. The factors of the leading coefficient are 1, 2, 3, and 6. Everybody's okay with that? Yes, of course. So, my possible rational solutions. It's going to be plus or minus a factor of the constant term over the factor of a leading coefficient. So the first leading coefficient factor is 1. So I'll take each of my constant term factors over 1. And the denominator is coming from the leading coefficient. So there's 4 possibilities right there. I need to write those as fractions, right? Since they're over 1, they're just whole numbers. But I could also have plus or minus 1 over 2, 5 over 2, 7 over 2, 35 over 2. Or I could have plus or minus 1 over 3, 5 over 3, 7 over 3, and 35 over 3. As well as plus or minus 1 over 6, 5 over 6, 7 over 6, and 35 over 6. So again, the numerators are always just the factors of the constant term. And the denominators are the factors of that leading coefficient. Well, that not readable at all, huh? Let's do that maybe. I need another color. Does everybody kind of see the pattern going on there? Now, let's look at what we have here with these 4 pieces, what we can do. All right. So we know every polynomial is solvable. Does that also mean that every polynomial is going to be factorable? Well, it depends on what our definition of factorable means, right? For us, we've been talking, when we talk about factoring, we mean factoring over the integers, where the coefficients of our factors are all integers. They're not fractions, they're not imaginary, they're not square roots or anything. They're just whole number coefficients, right? So if I know the solutions, maybe I can, like some of the solutions will give us factors, right? But some of the solutions could have square roots or fractions or imaginary things going on that wouldn't necessarily correspond to a factor. But I should be able to combine some of those solutions that don't fit as factors for us and multiply them together to get a new polynomial that would be a factor. You know what I mean? So like if one of my factors is x squared minus 2, that has the solutions of plus square root of 2 and minus square root of 2, right? I can take those 2 solutions, turn them into the factors x minus root 2 and x plus root 2, and I multiply those together, I get the x squared minus 2 factor. So in a way, if I can solve these, I can use the solutions to build out my factors, right? Is everybody okay with that? So that tells me if I can at least find the solutions, I should be able to create the factor for it. Everybody's okay with that notion? Okay. So the corollary to the fundamental theorem of algebra tells me the number of solutions I can expect, which is basically now going to be an upper bound on the number of factors I can have. Right? If something has 4 solutions, I could have 4 factors, but it might be that 2 of the solutions need to combine in to make me 1 factor, right? In the situation that I described before, where I had x minus root 2 and x plus root 2 multiply together to give me x squared minus 2, which is a factor that we'd use. Is that okay? So that kind of creates an upper bound on the number of factors I can have. The factor remainder theorem gives me a way to take, if I can find a factor, to do some of the factoring, right? We've used that already in the previous homework. What the rational roots theorem gives us is some place to narrow down the guesses in terms of what the factors are. Now, note that the rational roots theorem is not giving you all the possible solutions, just the ones that can be written as a fraction. So whole number ones can be written as fractions, and non-whole number ones, and then fractions obviously are fractions, like 1/2 or whatever. What's not going to occur on this list, though, are things that are irrational, like have the square root of 2 in it, and things that are imaginary that might have an I in it, right? Which is good because we can't use synthetic division with either of those 2 situations. Right? Because if I don't know the exact, anyways, like doing synthetic division with either one of those is not really feasible for us. So that's good. The problem is, look at how many choices we have. How many numbers are on that list? Well, I see 16 things listed, but they're all plus or minus, so there's really 32. Now that's like a 1 in 32 guess, which is a heck of a lot better than 1 in infinity. But I still don't love 1 in 32, right? That still sounds pretty crappy to me. That's a lot of potential failed synthetic divisions I'd have to try. Assuming that even there is a linear factor in there, which there's not guaranteed to be. Because that's the only thing you're going to find with the synthetic division are linear factors. That's okay. That's all we'd really focus on in this class. Is being able to get the linear factors out with synthetic division until you can get to a place where you can factor tree the rest of it. So hopefully, or the goal here now is to figure out a way to narrow down that list of rational roots, or narrow down that list from the rational roots theorem to make this a little bit easier to attack. Everybody's okay with that plan? Okay. Yes, sir. Yep. So to do that, I'm going to take advantage of some definitions. So I'm just going to really specify 4 really related terms, and we're going to use that relationship to figure out a good way to narrow down this list. Because you guys have a very powerful tool available to you that in my day I did not have available to me when I did this in high school, that makes this enormously more efficient. And we'll see that in a second. Okay. So for a polynomial f of x, we say that x equals a is a solution to the equation f of x is equal to 0. So what is that saying? You remember class when you solve for x, your teacher would ask you to plug it back in to check your work? Right? You guys remember doing that? That's all we're really saying. If I have a solution, I should be able to plug it back into the equation and it checks, right? Or if I have a number that I can plug into the equation that checks out, I know that number is a solution. Everybody's okay with that notion? Okay. So the next one, we say x equals a is a 0 for the function y equals f of x, if and only if f of a is equal to 0. So these two, okay. I'm just waiting now on my OneNote being laggy. All right, back to that. Zoom back out a little bit. So we say that a is a root for the polynomial f of x, if and only if f of x is equal to x minus a times some g of x, where g of x is so implied in here, so can be complex numbers. Roots, though, we're implying are only going to be rational numbers, because when we do write our factoring, we don't write, actually really we're writing, even. Because when we write our factors, we don't write them with rational coefficients. The type of polynomials we're talking about all have integer coefficients, so we're not going to have situations where our factors have anything other than integer coefficients. So the a's there really have to be integers. So what does that tell me then? Every root is a solution and necessarily going to be a root, right? For example, roots or zeros include imaginary things, and our roots aren't imaginary. Everybody okay there? Okay. Bless you. So our last one says that x equals a is an x-intercept for the graph of y equals f of x on the graph of y equals f of x. So here, when we talk about these a's that are x-intercepts, what kind of numbers can a be? Computer? Is those a's have to be real numbers, right? If it's a point on the x-axis, it has to be a real number. So what does that tell me about the relationship between my x-intercepts and the others? Well, every x-intercept is also a 0, and it's also a solution. But the reverse is not true, because zeros and solutions can have imaginary things in there. And we know every root corresponds to an x-intercept, but every x-intercept doesn't correspond to a root, because the x-intercepts can include things like square root of 2, that's a real number, but that wouldn't correspond to a root. Is everybody okay with the relationship between these four things? I think we covered what we needed to there. So how is this going to help us? Well, of these four things, solutions, zeros, roots, and x-intercepts, the thing that we want to find are roots, right? That's going to help us do the factoring. Everybody agree with that? If we can find all the roots, then we have the factoring done. Everybody agree with that? Okay, so that's what we're looking for. Of the other three, solutions, zeros, and x-intercepts, which is going to be the easiest one for us to find? It's a 1 in 3 guess, even if you have no idea. What does your gut say? From a practical standpoint, one of those three, solution, zero, or x-intercept, is going to be defined than the others. Which one do you think it is? Think about it from a practical standpoint. What would you have to do to find a solution? You have to solve, right? So if you have a polynomial, what do you have to do to solve a polynomial? We've only seen one technique to solve a polynomial in general, which is solving it by factoring. So if we could factor it to solve it, we could factor it to factor it, right? So solving's not going to be helpful. Everybody agree with that? Okay. And if zeros and solving are equivalent, do you think finding the zeros is going to be any easier? So what about x-intercepts? What would you need to have to find the x-intercepts? From a practical standpoint, what piece of information could I give you for you to figure out what the x-intercepts are? If you had a picture of the graph, could you do it? Do you have a way to get a picture of the graph pretty easily? What would you use? Your graphing calculator. This is something you have access to as a high schooler that I did not. And it greatly narrows down the possibilities. So the idea here that I'm getting at, we're going to use the calculator to find x-intercepts. We'll check those values. And we'll use the matches to do. So that's the general outline of here, what we're going to do. Because we know anything that's also an x-intercept necessarily isn't always going to be a root, but the things that are rational root theorems guaranteed are to be roots because they're all of the correct form. And we can do our synthetic division with those. So let's look at a couple of examples here of doing this process. Okay? I had that power strip, like command stripped to the side of my desk because all the cords are funny length and they all have these like stupid power converters and everything attached to them, and they're super heavy and are just a pain in the butt. And the command strip stopped holding like midway through the day today, and it's been driving me crazy ever since. I don't know why you'd have like a work desk like this without a power strip built into the side of it, where it's like really easy to put a power strip like attached to the side of your desk. Because all these stupid machines with their power converters attached to their cords, it's just a pain. You guys get it. Anyways, that's what I've been dealing with today, in addition to everything else that has to do with work. Okay. So let's look at some examples here. So we'll start with some relatively straightforward things. And then we'll move on to some things that are a little bit more ambiguous to kind of prep us for what we'll do in the next lesson, to kind of round out this procedure to deal with some of those weirder uncertainties. Okay? All right. So let's say we want to factor completely. We'll do a couple of examples here. Okay. So before I start doing any synthetic divisions, I'm going to look at three things to kind of figure out what I want to do. So I can tell right away that at most this polynomial has 4 solutions. How can I tell that? Its degree is 4, right? The degree is the biggest exponent. Everybody's good there? The rational roots theorem. So those are my possible rational zeros. Are going to be the factors of the constant term divided by the factors of the leading coefficient. Here the constant term is 24, so its factors are 1, 2, 3, 4, 6, 8, 12, and 24. And the leading coefficient is just 1. So my possible reasons there are just basically the factors of 24, because they're over 1, but like, who needs to write that as a fraction? I'm not about that life. You know what I mean, guys? And then what we'll do is we're going to look at the graph. So I'm going to fire up my graphing calculator. If it wants to open. Which I'm not sure that it really does want to do that for me. I'll try running it if this icon doesn't want to work. Is it already open or something? No. They're just going to be really slow and stubborn. Oh, did it open? Yeah, too many times, in fact. I'm just going to be the slowest computer in the entire world here. That's okay. All right. So I got my graphing calculator out. I did. Button. And I'm going to type in my polynomial exactly as it appears on my sheet of paper. Okay? So I just typed in my polynomial, just exactly as it looks like on my sheet of paper, into the y equals menu. And now I'm going to graph this, but I want to be careful about how I'm graphing this, because the parts that I care about are only these possible rational solutions, right? What's the smallest number on that list of possible rational solutions? Negative 24, right? Because they're plus, everything is a plus or minus. What's the biggest number on that list? Positive 24. So what I'm going to do is I'm going to pick my window to reflect that. The smallest x value that I care about is negative 24. And the largest x value that I care about is positive 24. The x scale I always want to leave at 1. And then the y's I'm going to pick to just make sure one is negative and one positive. I like to pick them pretty close to the x-axis because all I really care about is how things are crossing. I don't care what the rest of the graph is doing. I just care about where it's crossing in between those two x values. So I think that I get a better picture when I'm a little bit closer zoomed into the x-axis. So I usually pick something like negative 3 and positive 3 for my y's. So that's the window that I'm going to use. Once I've set my window, I'm going to hit graph. And now I see 4 x-intercepts. You saw 4 places where the graph crossed there. Now, so I know I have all of them that I can see because there's 4 solutions, right? So that's all of the possibilities. So I'm going to go ahead and get a closer look because I can't really tell what exactly those x values are from this view. But it looks like I can probably cut off all of this area and all of that area. So I'm just going to change my window down to like negative 5 to positive 5. That should be enough where I can read where it's crossing and still see everything. So it looks like I have negative 3, negative 1, positive 2, and positive 4 because each one of these little guys is a tick mark, is 1 unit. Is everybody good with how I read that? Okay. So I'm going to list those down now. So I have negative 3, negative 1, positive 2, and positive 4. And I'm going to check now to see if any of these are also on my RRT list. Well, negative 3 is, negative 1 is, positive 2 is, and positive 4 is. Everybody see that? So that means that any one of these would be a good place to start my synthetic division. It doesn't really matter. So I'm just going to pick one arbitrarily. Probably the easiest one to use from an arithmetic standpoint is the negative 1 because the multiplication is trivial. So I'm going to set up my synthetic division. The first step, I just bring that first number down. Negative 1 times 1 is negative 1. Add down, that's negative 3. Negative 1 times negative 3 is positive 3. Add down, that's negative 10. Negative 1 times negative 10 is positive 10. Add down, that's 24. And negative 1 times 24 is negative 24. Add down, and I get 0, which is what I was hoping for. So what this tells me then is x plus 1 is a factor. Where's the x plus 1 coming from? The fact that that gives me a remainder 0. Remember that this is like x minus a negative 1. So that's why the sign is flipping from negative 1 to positive 1. Is everybody okay with that? It'll always be that way. So it'll always be flipped like that. And then the other factor is going to come from that information. So remember that constant x coefficient, actually I want to put them up here, x squared, x to the third. Okay. Everybody so far so good? So a little bit more lead time in the beginning, but not after we've made our, after we figured out what we can use. It's basically going to be the same as the problems from last night, right? Okay, so we still need to try to factor the x cubed minus 3x squared minus 10x plus 24 a little bit more. Since that has 4 terms, if I could use the factor tree, I'd have to try to factor it by grouping, right? Take a look at that. Is grouping going to work on it? You should be able to tell that by just inspection, right? Can you guys see why it's not going to work? When you make your 2 groups and pull the greatest common factor, the leftovers aren't the same. So what do we do then? Well, we have to do a synthetic division on that piece, right? Does that mean we start all over and do the FTA, the RRT, and the graph? No way. Why not? Well, anything that was a factor for the original polynomial, any of the choices for factors for the original polynomial, will also be factors for its factors, right? So we've already used -1. So we'll just pick one of the other ones. We'll do 2, and we'll just do a synthetic division on that leftover polynomial. So I'm just going to do another synthetic division. I'll pick another thing from my list that I could possibly use and just try it again. And again, party time. So we still have the x plus 1 from before. We're getting an x minus 2 now. And then my leftovers is x squared minus x minus 12. And the x squared minus x minus 12 is something we can handle on the factoring tree, right? In fact, that's even better. That looks like a chapter 4 factoring problem. That should be easy to do, right? Well, how does that one factor? X squared minus x minus 12. Oh, come on. Adds to give, or multiplies to give me -12, adds to give me -1. Thank you. And since all of those are linear, we know that's exactly what we get. Feel okay with that? Okay, let's do another. Because sometimes weird stuff can happen. Of course. Let's think here. So let's say we have x to the 4th minus x cubed minus 2x minus 4. First thing you might think is, well, that's got 4 terms. Maybe I can just factor this by grouping, right? Worth checking. Is that going to work? No. Okay. So, on to our procedure then. So we know we have 4 solutions, so at most we have 4 factors. Our rational roots theorem is going to be plus or minus and just the factors of 4, right? Since the leading coefficient is 1. And if we look at our graph, let's see what we get here. Clear out the old one, and then just type in the new one exactly as it's written. Reset our window. What should the x min and x max be in this case? -4 and +4, right? Good. Because those are the biggest and smallest values from my RRT list. So hit graph. So I see, looks like -1 and +2. What do you notice that's a little weird about this, though? How many solutions can I have? 4. How many x-intercepts do I have, or can I see? 2. So what else could be going on? Where could those extra, what else could be going on? Right? Before they matched up, we had 4 x-intercepts and 4 solutions. Everything was straightforward. Here we have 2 x-intercepts, but 4 solutions. Where are the other 2 that we can't see? Well, there's a couple of possibilities, right? So one possibility is you can have 2 other imaginary solutions floating around because you're never going to be able to see those on your graph. That's possible. 2, you could have multiplicities, like those 2 solutions might be used twice, like x equals -1 might be a double solution, and x equals 2 might be a double solution, something like that. So that could be going on. 3, you could have an irrational solution that's bigger, smaller than -4 and +4 that's just outside of the viewing range that we can't see. Because, again, we are only seeing the rational solutions. You could have like the square root of 27 or something that's going to be outside of our viewing window. So that's basically one of those 3 things is going to be going on. Everybody okay with that idea? Now, next time we'll talk about how to kind of detect or do a better job of detecting what kinds of those things are going on. But for right now, we're just going to leave it as it is because I don't want to get too far down that road. So I'm going to just use the -1 to do my synthetic division. Notice when I'm setting up that synthetic division, I have that extra 0 in there. Why do I have that 0 in there? Yeah. So notice there are no x² terms in my polynomial. So when I set up my synthetic division, I gotta have that 0 in there for the x²s. If you do not include that, this will not work. You will not be able to get the right answer. There is no recovery until you notice that. But hopefully, when you tried this and the synthetic division didn't work, the fact that you'd be pretty sure that -1 is supposed to work would give you pause enough to go back and look and double check, like, did I screw up the synthetic division? And one of the things you should check in that case is there a 0 that needed to be there that I forgot to put in? Because it's easy to forget them. Number 1 mistake students make in doing this process is forgetting the zeros there. So that worked. Yay. So we're going to have x plus 1 times x to the 3rd minus 2x² plus 2x minus 4. So that second piece has 4 terms, you might notice that it is factorable by grouping. You could do that, right? Everybody see that? Or you could continue synthetically dividing. Either is fine. Let's pretend we didn't notice that it was groupable and just went ahead and go, well, we have another factor to use. Why not try it? Everybody okay with that plan? Again, you could have stopped and done the synthetic or the grouping there. But let's just pretend we didn't notice. And we know x squared plus 2 we can't factor anymore, right? I don't have to explain that, do I? I can if you need me to, but I'm going to save my breath if you guys are good. Because it's hard talking through a mask all day. All right, I think I have one more to try here. This will be the sneakiest one. So get ready for your sneakers. Even that last one, though, aside from when we sat down and thought about it, we have like 2 minutes left. What am I doing? I'm looking at the start time of 8th hour, not the time left in this class. I'm sorry. You should have said something to me when I started being like, oh, let's do another one. I don't have 15 minutes left. I have like 3 minutes left. So I do have an assignment for this, for what we've done here. It's homework 5. I'm going to drop that into the content library right now. That'll go in as part of Sunday's homework check. Do your best with this. There are some that get pretty sneaky. So don't be frustrated if you try synthetic division and it doesn't work because I've somehow managed to trick you into trying a synthetic division that wouldn't work. You may encounter that happening. Just move on and try a different one. Okay, doesn't necessarily mean you did something wrong. It just meant that Mr. Kulik was being sneaky and was trying to get you primed for the next lesson where we try to create some more tools to counteract when your teacher's trying to be sneaky and fool you. Okay? So yeah, this is the homework 5. It's got, a couple of these things. Some of them are quite easy. They're like one-steppers, which shouldn't be too bad. Some of them get a little bit sneakier towards the end. So just, yeah. Anyways, I'm done. So those of you at home, you can take off. We have a